In this video, I wanted to discuss how does the tabular method work for integration by parts applied to the integral of two functions f and g. Let's consider the typical setting. Let u be the first factor and dv to be the second factor g of x times dx. Then the integration by parts formula says that the integral equal to the integral of u times dv, which is u times v minus the integral of v du. Now we hope that the right-hand side integral is simpler than the original one. And on the right-hand side, we have du, which is the derivative of f times dx, and the v here, which is defined by this equation, to say that v has to be an antiderivative of g. So the choice for v is not unique, but that's for convenience, let's denote g1, where 1 is written as a superscript in brackets. So suppose this is g1 denotes any function whose derivative is g of x. In other words, g1 is just an antiderivative. And later, we're going to generalize this notation. So we're going to write the gn to denote any function whose nth derivative is g of x, where n can be any positive integer. So now we can replace u by f of x and the v by g1. So the first term on the right-hand side is f times g1. Now the integrand on the right-hand side is v du. So this is the v du, but v is what? V is g1, and du is f derivative of f times x. So let's rewrite the integral as the integral of f prime times g1, so that f goes first, no matter in the first term or second term. So this is a reformulation of the integration by parts without involving u and v. Okay, this is important, and we can easily remember this formula using this table. So notice that the left-hand side is the integral of the product of two functions, and in the first row f and g. The integrand on the right-hand side is the product of the function in the second row here. And the first term is the diagonal product, f and g1. So using this pattern, we can easily apply integration by parts without specifically defining what is u, what is v, because they're not involved in this formula. So here's an example. So suppose we wanted to integrate x squared times e to 3x, and we wanted to use integration by parts, with the first one being being our f, second function being our g. So what we do here is just to create this table with f and g in the first row. So x squared e to 3x. Then the second row consists of the derivative of f, which is 2x, and the derivative e to 3x. So we just integrate e to 3x and let the constant, integral constant to be 0. So we get 1/3 e to 3x. Now we're going to use this new formula to write out the result. So the first term will be f times g1. So it is this diagonal product minus the integral of the product of the function in the second row. So it is the integral of 2x and 1/3 e to 3x. So that's the result of the first application. We do not need to know to to think about U and dV. Okay, in a moment, we're going to finish this one, and you will see this new way is a lot simpler, especially if we needed to apply this method more times to an integral. And this is another advantage of this formula. It is expandable and it is reusable. So what I mean by this is the following. So let's the formula we just got. Okay. Now suppose we wanted to apply an integral by parts to the integral on the right hand side. Okay. Sometimes this is necessary. And what we do here is this: is simply expand this table 1 to table 2 by differentiating f prime, we get f double prime, and by integrating g1, we get g2. So we easily get this new table. And now we're going to apply the formula we stated here to the integral on the right hand side. So we're going to so the integral of this product, which is what we have here, is going to be equal to the product of the diagonal. So we look at this diagonal product, which is f prime and g2. Then minus the integral of the product of the function in the bottom row, which is here. Okay, so you see, we do not need to identify what is u and what is dv for this integral. We just use the same table and to write out the two terms for the second integral. So replace the second integral by those two terms. We get this new formula for the original integral with integration by parts applied twice. Now, if we needed to continue to use integration by parts, and there are many cases we do have to do this, we just expand this again by differentiating the second derivative to get the third derivative. By integrating g2, we get g3. And we can they convert this integral in the second row here as using integrated by parts, and the result will be here. Okay, will be the following three terms plus minus integral. And now here we can have a observation about the pattern, and this pattern will be used to generalize to more general formula, okay, where you need to apply this method to the integral n times, where n can be any positive integer. So let's look at the four terms. The first three terms, okay, they do not involve in integrals; they are already functions. So you notice that they are the three diagonal products: first diagonal product, second diagonal product, third diagonal product. F g1 times g1, f prime times g2, f double prime times g3. Okay, and then the last term is the integral of the product of the entries in the last row. And those four terms have alternating signs, plus, minus, plus, minus. So the pattern of these signs are also easy to remember. Okay, now suppose we, for any reason, we need to repeat this 5 times, 10 times, or n times. We can use the same pattern to formulate the formula. Okay, so let's go to the next page here. So if we apply this formula n times, we will get a combination of n terms plus 1, n plus 1 terms. And those n terms can be easily formed using this table. So we typically will, create this table first, okay, with f and g being the first row, and then we take derivative of f n times. We integrate g n times. Each time we integrate g, we set the constant c to be 0. And then we can form those diagonal products, and then the integral of the product of the functions in the last row. And then we combine those terms with plus minus signs. Okay, so that's how we do it. Yeah. We observe this pattern, but it can be actually proved, using, like, for example, mathematical induction or just by observation. Now, one application of this one is the following. If the function f, the first factor f is a polynomial, then when we keep taking derivative of f, sooner or later, we're going to get a 0, right? For example, if f is a quadratic function, and then we can apply this formula with n equal to 3. That means we use integration by parts 3 times. And notice that the last term, if would be, we know that the third derivative is 0, right? If f is quadratic. So that means there's no more derivative on the right hand side if we apply it with n equal to 3, which means that we're going to get an answer for this integral as a combination of 3 terms. Okay, and those 3 terms can be obtained by first creating this formula, and notice that the third derivative should be here, which is 0. So we only have 1, 2, 3 diagonal products, and we combine those 3 products with plus, minus, plus sign, and that's the answer. Okay, so there's no more u and v in this solution. Okay, that's pretty handy. And more generally, if you have a function f, that's a polynomial of degree m. Okay, and then we know that if you take the derivative of this function m plus 1 times, we're going to get 0, right? So that means if we apply the the formula above at the top of this page with n equal to m plus 1, then the integral will be 0, and so we only have the first n terms. And so here, this will be the formula here. This will be the formula. Again, we can easily form this combination of diagonal products using the table that we will create. So that's this new formula, and this method is called tabular method because it can be easily applied by using this table. So now let's look at some examples. You can see how easy it is. The first example, actually, I already worked out. Is number 1 here. It's an integral of 7x times e to 3x. So we will start with, creating this table. So with 7x is our polynomial, it's a linear polynomial. It has degree 1. E to 3x is g. So to create this table, we differentiate the function f successfully. So first derivative is 7, second derivative is 0. And we stop once we get 0 derivative. Now for the second column, we will integrate e to 3x successfully. When we integrate once, we get 1/3 e to 3x. When we integrate twice, we get another factor of 1 over 3. So we get 1 over 9 e to 3x. Now notice that in this case, we will only get 2 diagonal products. The first one is 7x times 1/3 e to 3x. And the second one is 7 times 1 over 9 times e to 3x. And the two terms have signs positive and negative. So in the middle, the sign is a negative minus sign. And we can simplify this by factoring e to 3x. And this will be the final answer. So here you see, we did not get involved in what is u, what is v, and so on. Okay, and we just needed to integrate the second factor twice. We can do it by heart. Okay, the second example, which is on the right side of the page, is the example which we mentioned earlier. Okay, it's the integral of x squared times e to 3x. It is something added here. And in this case, the first factor is the quadratic function. So we just do the same thing. We created this table with with f and g, the two factors being the first row, and then we differentiate x squared successfully. We get 2x, that's the first derivative, 2, that's the second derivative, and 0 is the third derivative. And for the second column, we integrate e to 3x. So we get 1/3 e to x, 1/9 e to 3x, and 1 over 27 e to 3x. And now we form the diagonal products. We get 3 products, right? The first one is x squared times 1/3 e to 3x. The second one is 2x times 1 over 9 e to 3x. And the third one is 2 times 1 over 27 e to 3x. And the signs of the 3 terms are plus, minus, plus, and so on. And again, we always add a constant to those functions. Okay, so now we can factor e to 3x. We get the final form of the solution. Okay. So let's finish with one more example, which is a little bit more involved. Okay, so the function first factor is a cubic function, but the method is really the same. So we're going to start with first look at this table. The table has 2 columns, right? And how many rows do we need? Well, in this case, this function f has a degree m, that's 3. And so the number of rows will be m plus 2, because we needed to take the derivative 4 times. And we also needed to write the top column for f and g. So this will be the table that we create. Again, the first the entry here is f. So we find its derivative, first derivative, 3x squared minus 5, second derivative is 6x, third derivative is 6, fourth derivative is 0. So this is the fourth derivative. Okay, then corresponding to the second column, we start with the second factor e to 2x. So we're going to integrate this successfully, and each time we integrate e to 2x, we will get a factor of 1/2. That's why we get 1/2, 1/4, 1/8, and 1/16, times e to 2x. So that's the first step. This step is really pretty routine, we just need to differentiate the first factor and integrate the second factor, and typically we can do them by hearts. Okay, so now we're going to form those diagonal products and combine them with alternating signs. So we're going to do this on the next page. So here, so on the top, I described what we're going to do now. And now we're going to form those four products here: first product, second product, third product, fourth product. And we're going to combine those products. So the original integral is given is equal to the combination of those four products. Okay, and then combine them with positive, negative, positive, negative sign, and then finally we add C to it. Okay, so you can check that. This is the combination of those products with appropriate signs, and then we simplify again by factoring e to 2x, and then we combine like terms, for the terms inside the parentheses, and this will be the final answer. Okay, I hope you enjoy this method, and this method not only works for the examples that we have here, which is the integral of a polynomial times e to kx, but also work for other integrals. And we are going to learn some in the future. For example, the second factor could be a trig function. And also there are some other cases which we will talk about in class. Okay, and that's all. I hope you enjoy this one.